Hello, this is Jack Jackson. In this video, we're going to be talking about optimization problems. So we're going to be using derivatives calculus to help us solve some optimization problems. And probably, arguably, this is perhaps the most important application of derivatives, or at least one of the most often used applications of derivatives, is this general class of optimization problems. So think about it. We often want to push something to the extreme. We may want to maximize something like revenue, or we may want to minimize our cost, or maybe minimize our average cost, or better yet, maybe maximize the profit. We may want to minimize the time or effort to complete a task, or maximize production levels, minimize materials used, maximize an area, or maybe maximize the volume available, maximize some measure of efficiency, minimize errors, or otherwise just get the most or least we can out of some function given the constraints of the situation. So optimization applications actually show up in extremely wide area applications in nearly any field. So before we get started, let's review a few things that we already know about functions in general. So the graph of a function can reach a local or global extremum only if one of the following occurs. The graph is at an endpoint, the derivative is undefined, or the derivative is 0. Okay, those are pretty much the only things that can happen. Alright, so the basic strategy in optimization problems is to basically find these places. So you want to write down a function that you want to optimize, and for what we're doing here, we want to get that as a function of a single variable. So this is single variable optimization. And so say you want to maximize volume, you want to get it in terms of a single distance measurement perhaps. Or maybe you want to maximize profit, you want to get profit in terms strictly of the quantity made, for example. So you need to write down that formula somehow. Sometimes the problem will just give it to you. They'll say it's modeled by this situation. Sometimes you might have to do some regression analysis, do like a linear regression or quadratic regression or exponential regression or something like that, and then use your regression equation to work with. It may be that you have to know something about the context of the problem. You have to know something about money or economics, or you might have to know something about geometry or something like that to write out what that formula is, or something about physics, for example. Then you want to identify the domain in the context of the problem. So you might have like a quadratic equation, quadratic polynomial function that is, and you know, just looked at that, you might say, well, the domain's all reals, but it may be that in the context of the problem that maybe only positive values are allowed for inputs and outputs or something. So there may be some constraints there put by the context of the problem, as well as constraints that are put there by the formula itself. Then you want to take the formula, compute the first derivative, set that first derivative equal to 0, and solve for these input values. Also identify any input values where the derivative is undefined, but the function is defined. For example, any places where you get a sharp corner or something. And then identify any inputs where you have endpoints. And then take all those x values, or input values, whatever the letter may be, and evaluate them, the original function at all those values. And now you have a table of x and y values at our sort of interesting points. Look for the sign of the derivative near these points, the sign of the second derivative near these points, and or a graph near these points to classify each of these points as a local maximum, a local minimum, or maybe neither one of those things. And then interpret your answer in context of the application. So a couple other things to remember is if the function is continuous and the domain in the context of the problem is a closed interval, then the function is guaranteed to have a local minimum and a local maximum on that interval. If those conditions are not there, then you're not guaranteed that it'll even have a maximum or minimum. So for example, the function may go off towards infinity or negative infinity It might have a minimum but not a maximum, or a maximum but not a minimum, or maybe neither one. So basically you want to use that strategy, and then go ahead and solve some application problems. So the first one that I want to look at is maybe appropriate because it's basically the situation Newton was looking at when he developed a lot of calculus. So he was interested in laws of motion and how bodies move. So if we have a body moving at a constant acceleration a, then let's kind of go from there. So in fact, the acceleration due to gravity is actually not constant. It's inversely proportional to the square of the distances between the centers of masses of the two objects. However, if an object is fairly near the surface, where most of us are likely to spend our entire lives, the highest any of us ever get is 4 or 5, maybe 6 miles up in an airplane. If we're going somewhere, even that's fairly close to the surface of the Earth. So it turns out that the difference between say that and sea level, for example, the difference in the acceleration due to gravity is very minimal. So basically we can consider ourselves as having a constant acceleration due to gravity near the Earth, and that is negative 9.8 meters per second square, or negative 32 feet per second square, is a 2 significant digit approximation of that constant. Okay, now so the acceleration due to gravity is basically the same. But a more significant influence is the effect of air. So if you've got an object and you drop it, will they hit the ground at the same time? Well, maybe. It doesn't depend on the mass of the object, but it does depend on some the effect of the air resistance, which has something to do with the shape of the object. For example, if you take a piece of paper that's wadded up in a tight ball and a flat piece of paper and you drop them, the ball is going to hit the ground before the paper, because the greater surface area makes the air resistance have a greater effect. So for example, on the moon, where there is no air, then the acceleration would be constant. It wouldn't be this negative 9.8 meters per second square. It would be a smaller number because of the smaller mass of the moon. Okay, so if we take an object such as a fired bullet or a thrown ball, we can assume acceleration due to gravity is constant and that the air resistance is very, very small, so it's pretty much can be ignored. Okay, so your acceleration in general is more or less a constant. So if the acceleration is the derivative of the velocity, so if the object has acceleration a constant a, what's the formula for the velocity going to be? Now notice I'm going a little bit backwards from something we've done in the past. See if you can figure this out. What would it be? Well, the acceleration is the derivative of the velocity. So this time we know the derivative is a constant. But wait a minute, we know that the derivative is the rate of change. A function with a constant rate of change must be a linear function. And so it's a linear function with slope a, and let's say the input variable is t for time. So it's a times t plus some constant. We're going to call that constant v sub 0 because v sub 0 is v of 0. If you plug in t equals 0, a times 0 is 0 plus v sub 0 is v sub 0. So v sub 0 is v of 0, the initial velocity. Okay, now what's a general formula for the position function for an object with a constant acceleration? So notice what we had to do here is I gave you the derivative and you had to find the original function v. So what we were doing was finding an antiderivative. Okay, we're going to be dealing a lot more with antiderivatives in our next playlist, next couple of playlists, next couple of units, but we're not going to do a whole lot with that here, but we are going to do this problem. So now we need another antiderivative. The antiderivative of the velocity is the position. So the velocity is the derivative of the position, and acceleration is the second derivative of the position, or the height. So we use P for position. Then we have P prime of t is V of t, P double prime of t is A of t. So remember that a quadratic polynomial will have a linear derivative, so what we're looking for is a quadratic polynomial. So notice if we make this 1/2 at squared, when we take the derivative, the 2 times the 1/2 cancels and we get at, which is the right first term. And then we need v sub 0 t for the second term, so when we do its derivative, it's v sub 0. And then we could have plus some constant p0. And again, p sub 0 is p of 0, the initial position, because when you plug in t, all these other terms go to 0, and so we get that. So now what we have is our position function is 1/2 at squared plus v sub 0 t plus p sub 0. The velocity is at plus v sub 0, and the acceleration is just a constant a. So if we have a constant acceleration, then this will be what we have for the velocity and position. Now in particular, if we're dealing, say, with the falling body problem, then this a is negative 9.8 meters per second square. So velocity is negative 9.8 meters per second square. V is then negative 9.8 t plus v sub 0 meters per second. And position is then, well, half of negative 9.8 is negative 4.9 meters per second. So it's negative 4.9 t squared plus v sub 0 t plus p sub 0. And that would be in meters. Or we could use it in the American units of negative 32 feet per second square. Okay, what's the optimal position when it does occur? The optimal position occurs when the derivative is 0. So that means the derivative of p, or v of t, is 0. So that's a times t plus v sub 0 is that. So we solve that. See, we subtract v sub 0 and divide by a. The optimal position, the maximum or minimum, whichever it's going to be, is when y equals negative v sub 0 over a. So that'll be the highest point that the ball reaches if we throw a ball up in the air. And that will be local and global minimum if the acceleration is negative, and of course that'll be a maximum. That'll be a maximum if the acceleration is negative, and it's a minimum if the acceleration is positive. So let's put this to work. Looks like I'm using American units here. Height of a ball as tall straight up is given by the formula. Well, that's going to be half a. A was negative 32 feet per second square. So that's going to be negative 16 times t squared plus 50t plus 5, where the height is measured in feet. Time is measured in seconds. Okay. Since its ball was released. Negative is going to represent downward. So what was at the height was the ball released or thrown? Is it thrown upward, or is it thrown downward, or is it just let go? Well, that's going to be your initial height. Height is y here. So I just put t as 0, and we get y as 5. So y of 0 is 5. So it was thrown from a height of 5 feet above the ground. What's the height of the ball 1 second after it released? We plug in 1 for t, and you see that you get 39 feet. The velocity is the instantaneous rate of change in height. What's the velocity formula? It's the derivative of that, which would be negative 32t plus 50. Okay. At what speed was the ball thrown? Well, that's the initial speed. And notice it's 50, and since that's positive, that's upward. The units are feet per second. So it was thrown upward at 50 feet per second, which is pretty fast. What is the velocity of the ball 1 second after release? Plug in 1 in that formula for the velocity, and that's 18 feet per second upward. So 1 second after we've thrown it, it's 39 feet above 39 feet above the ground. It started 5 feet above the ground. It's gone up to 39 feet above the ground, and it's still traveling upward started at 50 feet per second and still traveling upward at 18 feet per second at that point. So how high does it get? Well, the highest point is when the derivative of the height is 0, or in other words, the velocity is 0. So that turns out to be 0 equals negative 32t plus 50. So 32t equals 50, t equals 50 over 32, which reduces to 25/16, or 1.5625, and of course the units are seconds. So it's going to go upward for a little over 1.5 seconds. What's the maximum height of the ball? Take that t value, plug in the original height formula for y, right there. Take that original formula, plug in t equals that value we just came up with, 25/16. Don't round off at the end here. Now, do we know it that accurately? Probably not. We may want to round off our final answer, but don't round off anything in the middle. That's a general statement that you want to remember for any application problem. Don't round off values in the middle that's used for calculations. Only round off final values. And even if you round off something as an intermediate answer, use the non-rounded off version in further down the line. So, for example, if we rounded this off to 1.56 seconds, we wouldn't use 1.56 here. We'd have to use all these decimals, which is where this goes out to its terminator. Or better yet, just use the fraction version. So this turns, here it is in fractions, or here it is probably better in decimals. About 44 feet is how high it goes up. The acceleration of the ball is the instantaneous rate of change in the velocity. What is acceleration? And of course, it's negative 32 feet per second squared, which it always will be for a ball like this. When does the ball reach the ground? Okay, this is one where students have a little problems with. What do you know about it when it hits the ground? Think about this a minute. Well, if you're measuring from the ground, which we are here, you know the height is 0. The velocity is definitely not 0. I mean, if you were laying there on the ground and somebody threw something up in the air and it landed on you, you would definitely feel it because it would be moving when it hit you. You don't want that to happen. So it's the velocity is definitely not 0. Neither is the acceleration once it hits the ground. Now, after it hits the ground, it may just stick in the ground and stop at that point, or it may bounce, or it may even break apart. Who knows what happens at that point? It may sink in the mud. Who knows what might happen to it? But these formulas apply only from time equals 0 to the time when it hits the ground or hits something. Because, why? Why not negative time? It's not because negative time doesn't exist. It's because this equation modeling the height, and this one for the velocity down here and the other one for the acceleration, only applies to when we let the ball go and let only gravity act on it. So before that, the ball was, where maybe it was in our hand being moved around. So these equations would not apply there. And of course, after it hits the ground, then the equations no longer apply. So it has a very limited domain for this particular one in the context of the problem. If you just look at the formula, these are polynomial functions. It looks like the domain's all reals. But in the context of the problem, it's actually limited. So where were we? Okay. So what we know? We know that y is 0. The height is 0. So 0 equals negative 16t squared plus 50t plus 5. Well, we know how to solve those. That's a quadratic formula problem. So it's the quadratic formula is 0 equals a t squared plus bt plus c. Then t equals the opposite of b over 2a plus or minus the square root of b squared minus 4 times a times b over 2a. And we work that out. I have a tendency to write this as 2 parts here rather than 1 fraction. You may be more familiar with it with 1 fraction. That's fine too. In this case, we don't need an exact value anyway. We need a decimal approximation. So we'll work this out. I've written down all the digits my calculator had, but of course we'll round off at some point, whatever might be appropriate. Actually, our negative 32 feet per second is really only 2 significant digits, so probably we really only have 2 significant digits here in our answer anyway. So it's about 26 seconds, or about negative 29.5 seconds. Well, again, the negative seconds don't work here, again, not because negative time doesn't exist. Time didn't start happening once we let go of the ball. Okay, time existed before that. There was a time 29 seconds before, 0.5 seconds before we let go of the ball. It just that these equations don't apply there. So we throw that one out, okay, and we keep this one here. So the domain is actually from 0 to this 26.388 whatever seconds here is the appropriate domain. And so if we graph it, we only graph it from on that point. So we only graph for positive y's and positive heights. And then we only graph from 0 to really to that point there where it hits the ground, hits the x-axis. And if we pick an appropriate y, well, you can see it went up to the maximum height was 44 point something. We need to go up, I'd say, at least to 45. Here I went up to 50, and actually I went up to 45. And from 0 to 45 on y, and from 0 to OL I went just slightly past the time of 26.4 or something. I went just to no, the time was what? It's the wrong graph. Is that the right, or is that the right number? Hang on a minute. Now something's out of whack a little bit here. Let me double check here. So let's look at this. Let's put this in here and get a graph. Negative 16. We have to change to x's. X square plus, was it 50? X plus 5, and let's just graph this. Let's pick that same window and see if this is right. So this window says I only went out to about 3.5. If that's right, then I've done something wrong in that quadratic formula part. So let's okay, and I might as well just mark that in ones. And the y's, I can start at 0, and I want to go up to the 45 is right. Okay, that's pretty good. So something's off on this quadratic formula part. So let's go back here. The opposite of b over 2 times a. Aha. That's a negative 16. Here and here. Well, yeah, negative 16. So that makes this positive. That makes this from plus and minus. It's minus and plus, but you still get both options there. Okay, now let me check that arithmetic there. 50 b squared minus 4 times a times c. That's correct. Okay, so let's try that. 50 50 square minus 4 times a negative 16 times 5 . 2820. That's not even close. Okay, so that's how Got that out of whack there, but it's quite off. Double check here. Okay. So what I'm going to get is 25 divided by 16. Okay. Plus the square root of 2820 divided by 32. That's one of the answers. That's going to be the one the good one. Let's fix that. 3.221 98.756, at least as far as the calculator goes. And okay, and then we can take this and do second enter and change this to negative, to subtraction, I mean, here. Get the other possibility, which is going to be no good because it's negative. And it's negative what? 0.969897559. Okay, this should be better. Okay, let's get that out of here. Okay, so there we go. Those are the t values. That should be better. So it's about 3. Again, the negative one's not going to work, but the positive one will. About 3.222 seconds after release, or about 3.2 seconds later. The graph is, however, correct, so that's good. Okay, let's look at another example. Police department must determine the speed limit on a bridge such that the flow rate of cars is a maximum per unit time. The greater the speed limit, the farther apart the cars must be in order to keep a safe stopping distance. Okay, so experimental data on the stopping distance, D is our stopping distance, for various velocities, V, kilometers per hour, are shown in the table. So this is the velocity in kilometers per hour. This is the safe distance, how many meters you need to be between the cars in order to safely be able to stop. So if the car in front of you slams on your brake, this is, if you're closer than, like if they're going 60 kilometers per hour and they slam their brakes on, you're going to need 27.2 meters to react and put your brake on, slam your brake on, and stop without hitting the car in front. So if you're following more closely than that, and people follow very much too closely on many of the roads, then you're not safe. You're very likely to be in an accident. We're going to convert speeds to meters per second, and then get a quadratic function modeling the data. And we're going to assume that two consecutive vehicles are averaging 5.5 meters in length, and they're traveling safely over the bridge. Let T be the difference between when the front bumpers of each vehicle pass a given point, and let's get a formula for T. Okay. Use a graphing utility to graph T and estimate the speed that minimizes the time between vehicles. Use calculus to compute the speed and corresponding value of T exactly, and what's the optimal distance between the vehicles. So see if you can work that one out, and hopefully at some point I'll come back and put that answer in another video a little bit later on down the line. Okay.